Yes, so the topic of this session are exponential functions and logarithms. We will begin slowly by looking at how to find how to define the exponential function. We will just do it in an intuitive manner, but first of all, these seem to be zero, but they are not completely zero. They are only close to zero. And note that our y-axis is increased because otherwise things would disappear very quickly out here. So this is 20. To begin with, now we have base number a equals 2. So what is 2 to the power 0? Well, it's 1. This is 1. 2 to the power 1 is 2. 2 to the power 2 is 4. 2 to the power 3 is 8. 2 to the power 4 is 16. To the power 5, it's 32. 64, 108, and so 128, and so on, right? So these numbers you know how to find, right? So that's just the good old definition for any natural number. You just take a and multiply by itself n times. Right? This is what a to the power n means, if n is a natural number. So by definition, the empty product is always 1. So if you multiply a by itself 0 times, it's 1. So this should be 1. It turns out to be the sensible way of defining stuff. So now we know how to do it for natural numbers. How do we then do if we have integers? So what is an integer? Natural numbers are sometimes 0 is counted, but otherwise 1, 2, 3, 4, and so on. Integers are 0, 1, -1, 2, -2, and so on. All whole numbers, plus or minus. So either we know how to define it, or, that is if n is already positive, and if it's not positive, we can make it positive by putting a minus in front of it. And then we can use this definition. So a to the power n is the same as 1 over n to the power minus n. So if n is -3, right, we can just say, well, then it's 1 over a to the power 3, right? So that would be, for the case a equals 2, it would be an eighth, right? So the value here is an eighth, a 64th, a 32th, and so on. Now we know how to do it for integers, and the next question one might ask is, what do we do with fractions? If p over q is a fraction, so we write that as q, then we know how to find the qth root of a number. It's the positive number that to power q equals a. That's the qth root. So the normal square root is q equals 2, right? So what is the square root of some number? It's the positive number that multiplied by itself is what you wanted to take the root of, right? So this is well defined, and then you just put that to the power p. So this can also be defined at least for any positive a. These two definitions in fact work for any sign of the number a, right? This only works for positive a, and that's because otherwise you can't find a positive root, right? One could go into complex numbers, but let's not do that. So if we want to do that, now I look at q is equal to, look at how my points on this plane look. I'm basically putting in more numbers in between the integers, right? This all looks very natural, right? And of course, the point is that if you have any number which is not something you can write as a fraction like this, like square root 2 or pi or anything like that, you can approach this number to any as well as you want by just making your fraction appropriately made. If you want to have pi written as or something close to pi written as a fraction, you can just write 3, 1, 4, 1, 5, 9, 2, whatever, divided by 1, 0, 0, 0, 0, and so on, right? Then you get a fraction which is a good approximation of pi. And you can approximate it as good as you want. So any real number you can approach through a limit in Q, and then you can see if that process will lead you to a fixed number. So imagine you are pi, then you're somewhere here, right? And you want to see if you can be put in as a power. Then you just say, well, if I just let this Q here grow and choose P accordingly, will this number approach something? And as you can see from this, it seems to be the case, and in fact, it turns out you can do that, and then you get this graph here. Okay? So the result of that is what you call an exponential function. F of x equals a to the power x. In this case, a was 2, as I said. We can change that, right? If a is bigger, the function grows more quickly. If it's smaller, it grows more slowly. And you will see soon that something strange happens at some point. It's not strange, it's rather natural. First of all, if a is equal to 1, everything is just flat, right? Why is that? Because 1 times itself any number of times is just 1. And what is the root of 1? It's 1, right? If you multiply 1 by itself, it's 1. And that was the square root, but it applies to any root, right? So what happens if it becomes negative? Well, see what happens. We have takeoff at the other end. So if a is smaller than 1, we have a decreasing function. And if a is 0, then it's not defined for negative numbers. But that's basically exponential functions, right? Then, using just these properties, it's fairly easy to see that we have the following laws of exponents. So if you take a to the power r plus s, then it's the same as a to the power r times a to the power s, right? At least for these two, it's extremely easy to see. You have to work a bit more if you want to include fractions, and of course, if you want to have it for any real number, you have to go through this limiting process. But the good thing is it's enough to remember these for integers, right? And you can just test them using integers. If you can't remember, oh, what do I do if I have a to the power r and then I have to lift everything to the power s? What is this? Well, try with some number that you know, right? Try with a being equal to 2, r being equal to 2, s being equal to 3. What is a to the power? What is 2 to the power 2? Well, it's 4. What is 4 to the power 3? 4 times 4 times 4 is 64, I guess. So we should have that this is also 64. So 2 to the power what is 64? 2 to the power 6, right? So it turns out that we should multiply the 2 and the 3. But the nice thing is, because the way this is defined, I mean, this is designed. I mean, why do we do this like that? We do it because we want this rule to hold also for non-negative integers, or negative integers, of course. And the same goes for the other identities. So r to the power s is just the product of the exponents, a to the power of the product. And a to the power minus r is just 1 over a to the power r. Exactly as for integers. What if you multiply two numbers to the same power? Well, you can just put in the two numbers to the power separately and then multiply the numbers afterwards. Same goes for fractions. A over b to the power r is just a to the power r over b to the power r, which was something we actually used early on, right, for the sine and cosine and tan and so on, derivative functions. So that was the exponential function.